Welcome to this video. We're going to use this one to describe another relationship between electric field and electric potential difference. In a previous video, I showed how you could calculate the potential difference if you knew the electric field. It involved multiplication, or in the case of a non-uniform field, that multiplication turned into an integral, a calculus idea. So we're just going to do the opposite in this case. We're going to figure out what the electric field is from a known potential difference. So instead of using multiplication, we're going to use division. Or in calculus, instead of doing the integral, we're going to be using a derivative. But the processes are just inverses of each other. I think before we get too much into the calculus stuff, let's look at the simplest situation where we have a nice uniform field and we're trying to figure out what that field is. Now, sometimes you won't know what the uniform field is or whether the field is uniform until you take a look at the pattern of potentials. But what I have here, we can kind of see with two parallel plates that these have to be uniform fields. So here's how we use these division, or I wrote it as a calculus idea. What it says is if you move some distance through an electric field, the potential will change. And so we are going to look at how much the potential changes with each little move. So in the case of a uniform field, I think I'm going to write this with deltas instead of d's. They just look a little more familiar. So delta V and delta X. Another interesting thing about this is we're going to go from a scalar characteristic known as potential, and we're going to come up with an electric field measurement, which is a vector. So this is the first time you've probably seen going from a scalar to a vector, at least in electricity and magnetism. So here's what we do. We imagine starting someplace and moving through a field. So let's say we start on this potential line right here. That is, looking at the pattern, that's a 20 volt potential. And let's imagine we move over to here. So if we just write down what our change was, we moved from a 20 volt line to a 50 volt line. So that is a change of 30 volts. And what's our delta x? Delta x is how far in the x direction we ended up moving. Well, we started on the 1.5 centimeter line, and we ended up on the 6 centimeter line. So that's a move of 4.5 centimeters, or I'm going to call it 0.045 meters. Now don't forget to put the negative sign in there. I actually do that a lot. And then we'll do the calculation. And we're going to get about 667 volts per meter. And that is how strong the electric field is in the horizontal, or x direction. So now what about the y direction? I'm not going to write this, but I'm going to perform the same kind of operation. I'm going to imagine we move in the y direction. So if I go back to where I started at this 20 volt line and I move directly up, then how much change have I had? Well, notice I'm still on the 20 volt line, so that's a change of 0. So we get electric field in the y direction, E sub y, of 0. And because I'm on a two-dimensional screen, I can't really do the z direction, but I can tell you that these equipotential lines extend forwards and backwards, like into the screen as well, and so we'd also have no change moving in the z direction. So what that means is we have just a single number, 667 volts per meter, and it's all in the x direction. But now let's look at the sign here, because that has a negative sign that came with it. And what that tells you is that the direction of the electric field is opposite the way you moved through that field. So we moved rightward, and that negative just tells us that the field then is opposite that, or leftward. So if we were to draw this electric field in, then we would see nice parallel leftward lines, pretty much equally spaced apart, and that describes the electric field. 667 volts per meter or newtons per coulomb. Now, I don't need to write leftward, I don't need to say in the x direction because the figure already takes care of that. So that is the way we get a measure of the electric field from using the potential pattern. So what happens if we have a non-uniform field? I think because I've already created a pretty thorough description of this, I'm going to refer you to that. And it'll be, if you're on the YouTube channel, on the same channel, or if you're in my class, it'll be on the Google Classroom site or wherever we're storing our videos whenever you watch this. And it uses the idea of partial derivatives, which is kind of like what I've shown up here. You just do three different problems. You take a derivative where x is your variable, a derivative where y is your variable, and a derivative again where z is your variable. So you just have three derivatives to do instead of one. It's not any harder than doing any other derivative. You just do it three, and that's how you get the three components of your electric field. So if you can't find a reference and you want to look at the video for that, I think that's probably a better suggestion. So we're going to stop that here, and hopefully you got what you needed, and you can move onward in your study of electric fields and potential.